Okay, so this video is going to cover wave interactions. So the first thing we're going to look at is something called wave interference. So two pieces of matter can't occupy the same spot. So you can't put you and your friend in the exact same spot, but because waves transfer energy, not matter, they can occupy two waves can occupy the same spot at the same time. This is called the superposition principle. So superposition means that two waves can occupy the exact same space at the same time. You know this to be true if you ever listen to two people talk at the same time. Those waves can overlap. Okay, so when waves overlap, they undergo what's called interference. So when waves combine, they have interference. Now this only happens if the wavelength or the frequency of the wave is the same. As long as these wavelengths are the same, you get interference. The example here is called constructive interference. So in constructive interference, the waves are on the same side of a medium, and often what happens is one wave will go forward, hits a surface, and reflects back. So you have two waves moving in opposite directions that hit each other, and they make a bigger momentary wave. That bigger momentary wave is called a constructive interference. It's only a momentary thing, but you get a bigger wave momentarily when these wave crests overlap with each other and make a bigger wave. Destructive does the opposite. So you have a crest and a trough that overlap, and they make a momentarily smaller wave. Now you can imagine if a crest and a trough were the exact same height, they would completely cancel momentarily and you have no wave. So destructive interference, the waves are a crest and a trough overlap to form a smaller wave. So here they are side by side. If you have a crest, two crests overlap, two troughs overlap, you get a much bigger wave. The crests add together, the troughs add together, you get a bigger wave. That's constructive interference. If a crest and a trough overlap, they subtract, and if the crest is completely the opposite height of the trough, you get a completely destructive interference. Okay, so now we're going to look at a special type of interference called a standing wave. So it's a pattern that results when two waves that have the same frequency, wavelength, and amplitude travel in opposite directions and interfere. So standing waves, they have to pretty much have the exact same wave interfering going both ways. That's different than a constructive or destructive interference. The amplitudes don't have to be the same. So standing waves are what are called nodes and antinodes. So a node is a place where you have zero displacement, and an antinode is where you have maximum or biggest displacement. So again, only certain wavelengths can make standing wave patterns. If we look at this is you can imagine like a guitar string. So the waves are actually bouncing back and forth on this. And the spots at the end where there's no wave movement, those here at the ends are nodes. So in letter B here, we have two nodes, and this bulge in the middle is the antinode. So you have destructive interference where they cancel out at the ends, constructive interference where they have the maximum displacement. This letter B is only half of a wave. A standing wave needs to look like letter C. One standing wave is like a figure 8 pattern. So B, if we look at everything in terms of this L here, letter B actually has a wavelength of twice the length of the string, or 2L. B is going to have a wavelength, since there's two antinodes here, it makes one complete figure 8, has a wavelength of L. Letter D here is a wave and a half. So this wavelength is actually 2/3 of L. So this one shows 4 different standing waves. Waves going back and forth. And as they vibrate, so this is the longest wavelength. This is the next longest wavelength. This is the next longest wavelength. This is the shortest wavelength, where it makes 2 standing waves. But if you notice, the wavelengths are actual multiples. They can only be certain multiples. So like we can have a half of this one is half a wavelength. We can't do a quarter of a wavelength because that would be like this long. And you have to have 3 nodes per standing wave. So we can't make one that's like this long here because we can't make a node. So they have to be half, what they call half integers. Okay, so I'm going to make a standing wave on this. And if you notice, this wave oscillates back and forth. And we're going to do it right here. So if we go in slow motion here, the areas that bounce up and down, so here, 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 those are your antinodes. The spots that look like they don't move, when it oscillates, the spots that don't move, those are your nodes. So we have for sure a node here and and nodes over here. And what's going on here is that actually this interference is creating some interesting patterns. But if I pause this, and I change my frequency, so I reset this, I'm going to actually turn off what it's called dampening here. And I just do this. So if I can set it, if I don't get the right frequency, I get this jumbled pattern. But if I make it oscillate at a certain rate, you can see the up part, those are areas of constructive interference. Where they cancel here, these little dots don't move. We gotta get this thing reset here. All right, so we have these bulges, where your areas of constructive interference, and where they cancel out as your areas of destructive interference, your nodes and your antinodes. So this one basically makes 1, 2, 3, 4 nodes, and so 4 nodes would actually be 2 standing waves. I'm sorry for the confusion on this. Okay, but if you have the bulges, those areas of constructive interference, those are your antinodes, and the spots where they don't move, those are your nodes. And we're going to stop the video there. Make sure you answer the questions on the Google form, and we'll see you in class. Bye-bye.